Hello, my name is Alexey Turin, and I am a master student at St. Petersburg State University, and this is a short talk video for the poster session at ICFP Students Research Competition. I'm currently working on a project which aims to add support for fusion optimization for sparse applications, while eventually generating hardware code for them to achieve performance, and in this video I'm going to elaborate on that. Fusion is an important optimization to reduce the number of memory accesses, and it is widely adopted in dense applications, for example, in TensorFlow. In a nutshell, if we have some chain computations that involve matrices, for example, in a traditional way of execution, it is needed to first compute the result of the first two matrices, creating another matrix, and then iterate over this new matrix again to compute the final result. Such a matrix in the middle is considered an intermediate data structure, and the purpose of fusion is to eliminate them. So fusion generates a procedure that takes three matrices at once, thus reducing the number of kernel calls and merges the operations in a way such that no intermediate matrix occurs. So there is a new operation that takes three arguments. Considering another example where a mask that takes only a subset of the result is applied to operation, mask fusion explicitly reduces the number of memory accesses, namely from 16 to 8. However, such optimization is hard to implement for sparse computations, since sparse data structures have non-regular memory accesses. The problem of intermediate data structure is well studied in functional programming, where fusion is often referred to as deforestation. So we opt to use purely functional representation for sparse data structures, namely quad-tree representations that allow us to code sparse linear algebra algorithms in a composable recursive manner. Such a representation just splits recursively a matrix, for example, into four submatrices, having a specific notion for empty submatrices to save memory. This allows us to use distillation to implement fusion. To reduce the overhead of functional language and achieve the performance of modern sparse frameworks implementations in C and C++, we synthesize FPGA kernels from our functional programs that are highly pipelined in parallel, allowing us to implement quad-tree representation in hardware in whatever way we want. We utilize a hardware compiler from FHW project for this. On top of fusion, distillation also performs partial evaluation if some static data is present, yields tail-recursive modular clones programs where every function call is tail-recursive, except that it could be wrapped in constructor application. This implies less requirements for garbage collection and eases the translation into hardware. Finally, distillation is able to produce superlinear speedup for input programs. We use distillation, authored by Jeff Hamilton, and its functional language to evaluate the approach in terms of reductions and memory accesses. So for the first software evaluation, we have chained element-wise additions, like in the first example, and the other two are Kronecker products of sparse matrices with a mask, either trigonal or diagonal, like in the second example. On the x-axis, we have the number of non-zero elements in our matrices, and on the y-axis, we have either the logarithm of the number of reductions or of memory accesses. It could be seen that distilled programs are up to 60% more effective in terms of reductions and 45% in terms of memory accesses. For FPGA kernel generation, we use the FHW project, and the only evaluation example at the moment is element-wise addition. For the hardware case, on the y-axis, we have the number of clocks in simulation and the number of memory writes. Such low number of non-zeros are due to the fact that there is no support for external memory at the moment, and to be able to count the number of memory writes in simulation. It could be seen that the distilled program is up to 20% more effective in terms of clocks and memory writes. Thus, the main contribution of this work is the idea to utilize functional representation and distillation to support fusion and hardware generation to increase the performance. Also, thanks to this project, the distiller and the hardware compiler are now in some working state and are available in the corresponding repositories. So for you to stay tuned, here's what is planned. We plan to move the distiller from proof of concept to ready to use, also move the hardware compiler from proof of concept to ready to use, and bridge the gap between our approach and existing sparse frameworks in a form of open cell-like kernels. Also, more real-world example revelations are coming. Thank you all for watching.